A neural network consists of nodes and connections between those nodes. There are three layers in a neural network. There's an input layer, one or more hidden layers, and an output layer. In this example, we have an input layer that has two nodes, and each node corresponds to an input variable. In this example, we're assessing how fat content and salt content in cheese relates to whether people dislike or like the cheese. So at the input layer, we have a node for the fat variable and the salt variable. And then on the output nodes, we have one node for disliking the cheese and one for liking the cheese. So when we're doing something like this where we have a binary outcome variable, then we'll assess the strength of the dislike or the negative and the positive, in this case like. So what we're trying to do is we have known values of fat and salt, and we have known values of how much people like or dislike the cheese. And so what we want to do is we want to train the network to be able to do a good job of bridging the gap between these values and the output values. The way neural networks work is that you connect the inputs to the hidden layers. So in this case, this node 1 would connect to all of the hidden layers, and so would node 2 would also connect to the hidden layers. And then at each node that is not an input node, there is also a bias, which is sort of like a random intercept that is added into the calculation. And so basically what will happen is whatever the value of the fat variable is will be multiplied by this weight to go to node 3, by this weight to go to node 4, and by this weight to go to node 5. And the same thing will happen in terms of salt. The value of the salt for this particular piece of cheese will be multiplied by this weight to go up to this node, by this weight to go here, and by this weight to go there. When we have a non-input node that has the value of the various input variables multiplied across the weights, then the product of these multiplications are then brought to this node, and they're summed up with a randomly assigned bias value. And so in this case, we would have 4 different values added together into a sum, and then that sum is used as an input to a function that will convert that sum into a different output. So for example, if all of these added up to be some sort of value for, say, legit in a logistic response function, then we would take this value that is the input for legit, and when we would run it through 1 over 1 plus e to the negative z, and then a probability output would come out the back end. So now that we have the basic idea of what's going on in the neural network, let's take an example. In this example, we have a fat value of 0.2, we have a salt value of 0.9, and then in this particular case, the outcome was that the cheese was liked. And so the probability that was liked was actually a 1. People did like the cheese. And so basically, when we initially did the calculation by running it through the neural network, we had 0.503 as the like and not 1. And so basically what we want to do is we want to show how these values and the influence of these values of fat and salt are passed through the network and how the calculation is done. And we want to do it with real numbers instead of just looking at symbols. So in this case then, the input for this particular cheese is 0.2 for fat, 0.9 for salt. These values on the weights were randomly assigned by the neural network. Also, the values for bias at each one of these functions was randomly assigned by the neural network, and you'll notice that they tend to be small values. And part of the reason for that is because if you have larger values and you multiply them by small values, then you don't get especially large values on the output side of these nodes. And so in this case then, I have done the calculation for getting this 0.45 on the output of node 3. First, let's start with the intercept. We have this bias function of negative 0.02. So here's the negative 0.02. And then we're going to take 0.2 times 0.05. So there's the 0.2 times 0.05. The other input that's coming into node 3 is 0.9 times 0.01. So there's the 0.9 times 0.01. Now, we're using the logistic response function here to be able to translate all of these various weights, including the intercept, into an output. So what's happening at this node then is we're collecting these various values, summing them all up, and then we are plugging them into the logistic response function. And so this math right here sums up to negative 0.181. And then when we run that value through the logistic response function, we come up with 0.45. So on the back side of this node then, we have a probability of 0.45. And so that's the value that we got when we went through this process. Then we would continue on moving forward. So now we have 0.45, and so now we want to calculate the value of dislike. What's the probability of dislike? By taking 0.45 minus negative 0.01, and then taking 0.58 times negative 0.015, and taking 0.55 times 0.01, and adding into this bias function, then we're going to get the number that is going to be run through the logistic response function and produce 0.497. And I have the math for that here. So here we have our bias. We have our 0.45 times negative 0.01, our 0.58 times negative 0.015, and our 0.55 times 0.01. Those all add up to 0.018. When we raise e to the negative 0.018, add it plus 1, take all of that under 1, then what comes out the back end of logistic response function is 0.497. So that's an example of how we calculated the dislike. And we would go through the very same process of taking all of these that are going to the various hidden layer nodes, and then take these values and multiply them through and get these. So what have we learned? We have known values for the input layers. We have known values for whether someone really likes or doesn't like the cheese that is in question. In this case, they did like it, so we came up with 0.503 for a like and 0.497. So even though this is greater than 0.5, it's still quite a ways away from the one that we expect to receive here. So what would happen then is the neural network would feed backwards, and it would say, all right, I've got 0.5 here, and what I was expecting was 1. And so what it would do then is it would go back and it would randomly change the weights on at this layer and at this layer. And because it's off by quite a bit, it would make large changes in these weights. And then it would run through the network again and see if this value is closer to 1. And if it still was a big distance, then it would also go back and make big changes in the network, and it would keep going through this process until what it comes with on this end would be something very close to 1, and in this case would be something very close to 0, or it might be 0. And once it finds something, these various weights that allow the multiplication to go through the network and come up with what is expected, then it will stop training. It will stop feeding back changes through the network. And so that's how a neural network learns. It basically will go through these various connections. It'll go through the math, be able to transfer influence across these connections through the nodes in the hidden layer to the output nodes, see how far off it is, and then it will go back and propagate these various changes in the weights back through the network, and it will iterate and progress until these values are so close to what it's expecting that it decides not to propagate changes back anymore. There's a significant random component to generating these neural networks, and that is because the values for bias, as relating to each of these functions that does a conversion from inputs to outputs, and the value of the starter weights on the links between neurons are randomly assigned. Because of this, a person might do 50 neural networks and each one will start at a different place. Now, that's not necessarily a bad thing, because even though they start at different places, they can often learn their way forward and do a fairly good job. But still, one of those networks is going to tend to be a better outcome or a better solution than the others. And because this random process means that sometimes we're going to start at a bad start, a place that is sort of bad for training the network, and others will start at good places to begin, it's good to be able to have multiple neural networks. And tools like JUMP, these are called TORs. And so when we're setting up our neural network, we may want to do 20 or 50 or 30 different tours. Then the tool will pick the best of those and give that to us as the preferred solution.